Okay, the question is from page 6, number 6. Okay, so it says the polar curve is given by r equals 5 over 3. So again, page 6. Polar curve is given by r equals 5 over 3 minus sine theta. What angle theta corresponds on the curve with a y coordinate of -1? And the interval is from 0 to 2 pi. So first, we get everything in terms of y and x, or in terms of replace the r with theta, and we get y is equal to 5 sine theta over 3 minus sine theta. Okay. We're basically looking for when is y equal to -1, the theta that corresponds to it, and so we replace y with -1, cross multiply, and we try to get theta by itself as close as we can. So 4 sine theta equals -3, sine theta equals -3/4. And we just solve for theta. And there's not a unit circle value, so we have to use our calculator here. So theta is equal to -0.848. But this tells us that we know this is going to exist. Sine is going to be negative in the third and fourth quadrant, right? Okay. So if we get theta equals -0.848, that's indicating to us what the reference angle is. Okay. I know it seems kind of abstract, but let me give you another example here. Let's say I had see mode. This work. Okay, this could work. Okay, let's say I did a unit circle value. Okay, inverse sine of -√2/2, right? Where is sine equal to -√2/2? And then in the calculator, it will give you this in degree mode. This will give you -45. Okay, let's think about that. So -45, that's telling us that it's in the third and fourth quadrant, right? And then we know that 45 degrees is the reference angle. So if I want to find the 45-degree version of the third and fourth quadrant, I will do 360 minus 45, or 180 plus 45. Right? And so because this is the reference angle version of that fourth quadrant, of that first quadrant, I just have to figure out how to get into that fourth quadrant. So I do 2 pi minus 0.848, and then pi plus 0.848. I know degree makes more sense, so I think that is probably an easier way to think about it. Okay, I think I just want to kind of run through worksheet 3 and just talk about each problem briefly, and then you guys can stop me if you want me to go any. Yeah, so if you're online, just just get my attention through putting in the chat or turning on your mic and let me know that you want me to, or you have a question about anything. Okay, so I'm just going to start on page 9 and just kind of talk through these problems. So number 1, what is the slope of the tangent line to the curve parametric by x equals √t and y equals 1/4 t squared minus 4? So this is just really finding order pair and finding slope. So we know x and y equation. We have the t value, so we can just plug in and find our. Well, actually, we already have our order pair here, x and y. But we have to look for the t value, basically. Okay, so we have our x and y value. We have to solve for find t. So we can replace x with 2, and then we solve for t. We get t equals 4. And then we solve for y, and we just have to make sure that that at order pair 2, 3, that we can find a time value that's consistent, because, you know, X and Y may have different T values where they hit these X and Y values at different points or at different times. So just to confirm, both X and Y are going to hit 2 and 3 at this T value. So that's good. We want to have that consistency. And so we know our T value is 4. That's what we want to use. So then we just have to figure out what is the slope of the tangent line when T is equal to 4. So we just have to do Y prime over X prime, and Y prime and X prime, we can just go through power rule for each. And then once we have power rule for each, we do dy over dx, clean that up, replace all the T's with 4, and then we find our slope of our tangent line. All right, number 2, what is the second derivative? So second derivative has a very specific format. We have to first find dy dx, and then we have to find the derivative of this divided by dx d theta. So first x prime, y prime. X prime is cosine, y prime is -2 sine. We do y prime over x prime, clean that up, we get -2 tangents. So now we're at our dy dx, but the second formula is the derivative of this divided by x prime. So the derivative of -2 tangent is -2 secant squared theta divided by x prime. X prime is cosine theta. We don't want to change this, just keep it. And then we just clean it up as much as we can. Bring that cosine up as secant, so -2 secant cubed.
For number 1, do you have to make sure they have like T equal?
They do, yeah. We have to make sure they're at the same T
So if they
value.
weren't, would you just stop?
Right, you would stop. But you know, the way that the problem is built, you're gonna get a T value. You just may have, you said, yeah, just make sure that, you know, there could be more than one for each of them, but you just have to make sure that you want to find the time that lines up for both the X and Y.
So you just plug it into the like basic.
Yeah.
equation,
Don't
solve
do any
for T,
derivative, just solve for T for
and then
both.
for the slope, you get the derivative dy dx.
Yeah.
And you plug that value that happens in for the slope.
Yeah, replace the T value that you found into the slope formula. All right, number 3, length of the parametric. So here's our length formula in parametric form. So integral from a to b, x prime squared plus y prime squared. So as soon as we have x prime, y prime, we should actually get it into that form. Okay, number 4. The position of a particle in the xy plane is defined by a vector valued function, f of t, is in the vector form here. For what values particle at rest? Particle is at rest whenever our velocity is equal to 0 for both the vertical and the horizontal component. So it could be not moving for the horizontal, but still moving for the vertical. So we want to make sure that we can find a time when both have a shared t value where they're both at a stopping point. So we find our velocity component, our velocity or our f prime vector, and then we set both equal to 0, and we solve for t, and we look to see when are they both going to be stopped. So they're both going to be stopped at t equals 6. So that's going to be when the particle is at true rest, when it's not moving horizontally, when it's not moving vertically, t equals 6. Okay, number 5. Time t between 0 and 2 pi, the position of the particle is moving along the path in the xy plane. Find the slope of the particle. So we have our x and y component of our vector value function. So to find the slope, we have to do x prime and y prime and then divide them by each other. So x prime, we got to go through product rule. x, y prime, we also have to go through product rule as well. So f prime g plus fg prime. Here, I'm just going to get my x prime of pi over 2 out of the way, because ultimately at the end, I have to do y prime of pi over 2 divided by x prime of pi over 2. So x prime pi over 2, I get negative e to the pi. Y prime, I go through product rule again, plug pi over 2 in. I get 2e to the pi. For dy dx, I just divide y prime divided by x prime, and I get down to a number, and that's my slope. Okay, page 10, number 6. At time t greater than 0, greater than or equal to 0, particle moves in the xy plane with a velocity vector of v of t. Particle is at point 1/1/2 at time t equals 0. How far is the particle from the origin at time t equals 1? So what we can do is we can figure out how far this particle moves from a horizontal perspective and from a vertical perspective. So we can use that final position equals initial plus displacement. We have our vector component, our horizontal component for our vector, for our velocity vector. And then we also have a starting point for our x coordinate. And then from the y component, we have the velocity of our y component, and we also have the starting location of our y. So we just think of it as two separate problems. We just have to find our final position from our x and the y perspective. So x of b, my final position equals initial plus displacement. So x of 1 equals x of 0 plus the integral from 0 to 1 of 2 dt. Okay. This one we can do by hand or make your calculator do it. And then this is x of 0 is 1. So we know that from our x coordinate perspective, we end up at x value 3, 1 second into 1 second into this particle's motion. Okay. For y, y starts at 1/2, and then it makes a progress vertically 0.8100. And then so we know what from y perspective, it's going to be at 1.310. So if we start at 1/1/2 and we end at 1.3, they just want to know how far is this from the origin. So we just have to do the distance formula comparing this with the origin. So my distance from the origin is x of 2 minus x of 1 squared plus y sub 2 minus y sub 1 squared, and then distance formula. Or if you want to, you can draw Pythagorean theorem and just find the hypotenuse between 0 and 0 in the order pair 1.3, right? A squared plus b squared equals c squared. Solve for c, hit the square root, same thing. Okay, total distance. Okay, total distance looks a lot like your arc length. Right, basically, very similar formula here. So we have to just find x prime and y prime, go through power rule and chain rule. And then once you have x prime and y prime, we insert into our distance formula. And then the rest goes in your calculator. I think we're on page 10. We're going through worksheet 3. Okay, number 8. The velocity vector of particle moving in the xy plane has components given by dx dt and dy dt. At time t equals 2, the position is 3, 2. What is the x-coordinate of the position vector? So we know final position equals initial plus displacement. And yeah, this is, we know the formula, we just have to adapt it for our x of 3. Okay, number 9, particle moves along the polar curve. R equals 4 minus 2 cosine theta, so that d theta dt equals 4. Find the value of dr dt. So this feels like a related rates problem. We just find the derivative, get all the t's to show up. R becomes dr dt, cosine theta becomes negative sine theta d theta dt. And once we have our equation, then we just make a bunch of substitutions and solve for the variable that they want us to solve. So R becomes dr dt, 4 becomes 0. Negative 2 cosine theta becomes negative 2 stays. The cosine becomes negative sine. And then we find the derivative with respect to time. So d theta dt. Okay. So d theta dt is 4. We make that substitution. And then we're just trying to solve for dr dt. Unit circle values, sine of pi over 3 is just √3 over 2. So 4 √3. Okay, number 10, for certain polar curve R is equal to f of theta, it is known that dx d theta equals 3 cosine theta minus 3 theta sine theta, and dy over d theta is equal to this. What is the value of the second derivative at theta equals 3? So here's our formula for second derivative. It's the derivative of my dy dx all over dx d theta. So we have dy d theta, we have dx d theta, it's a mess. We can just make it a two-step process here. We find the derivative of this at theta equals 3. So you don't have to go through all the theta. You can just leave it in terms of x. You can do math 8. Math 8 of this at 3, you'll get 5.5067. And then you do math 8 of the denominator here at x equals 3, you get 8.0632. And then you just divide them out. Okay, the graph shows a polar curve R is equal to 2 plus cosine theta from 0 to pi. What is the area of the region bounded by the curve? So 2 plus cosine theta, they tell us is from 0 to pi, but even if they didn't tell that to us, we should be able to figure out by using table of values. And you can also use your calculator. You can kind of trace along. If you want to trace along, make sure you guys are good with that. So first, you're going to be in polar mode. And another adjustment you may have to make, I think this will be helpful as well. If you do second zoom, it'll take you to format, and you want to be in polar graph coordinates. That way, you're not seeing x and y when you trace. You're seeing r and theta as you trace. Okay, so second zoom will take you to format and select your polar GC instead of rectangular GC. So now if you go to y equals, you can do 2 plus cosine theta. A graph. Maybe zoom 0 is going to be a place that will help you get the graph to show up better. Okay, let me try another one. Zoom 9. Here, zoom 6. Zoom 6 is maybe better. And then if you do trace, you can go to the right, and you see that as you move to the right, that when it gets to the halfway point, oh, sorry, I should be in, let me go to the trace. Let me be in radian mode instead of degree. Oh, something is messed up. Yeah, let me try again. Two plus cosine. Okay, so when I hit trace, move to the right, it should, by the halfway point, it should be. Yeah, 3.14, right? That makes sense. That halfway through we're at pi. So you can use that approximation from theta in terms of radians to help you decide where you are. But yeah, we can also use our table of values to convince ourselves that this from one end to the other is half a circle. It will be it's going to be take pi radian measure to get there. So we just have to find area. Now, remember area, we're always sweeping out in a counterclockwise motion. And we're always sweeping out from the origin out. And it's always going to create these sectors or these wedges in this. And as it hits the graph, that's the graph that we want to use. And you kind of see all these infinitely thin, imagine all these infinitely thin wedges or slices. Okay, so you didn't have the same number of open parentheses as you have closed parentheses. So it looks like you have 1, 2, 3 open parentheses, but you only have 2 closed parentheses. So maybe you need 1 more closed parentheses here. There we go. Remember the area formula for polar area for polar region. Polar area formula is 1/2 integral from theta 1 to theta 2 of r squared d theta, and the rest goes in your calculator. Number 12, find the area of the shaded region. So I just started out to convince myself that I knew where this graph was starting. So at 0, this graph starts at 0. At pi over 2, it ends up at 1. So that tells me that's exactly what I want from my interval, right? I know this graph isn't starting in a weird location. And it's always a good idea to just start off your table of values or look in your calculator and make sure that you know where the graph is starting. And that can kind of help you just have some assurance that you're not accidentally picking the wrong theta value as you're building your area. So this is going from 0 to pi over 2, and we're adding these infinitely thin sector regions from this all the way from here to here. Okay, and then we just do 1/2 integral from theta 1 to theta 2 of r squared d theta. Okay, so if we trace in our calculator, we're going to see that this whole thing takes 2 pi to complete. And because it takes 2 pi to complete, we know half of it will only take from 0 to pi to complete. You can use table of values, you can use your calculator. But because we know half of it takes from 0 to pi, we can just set that up from 0 to pi, or you can just do the full thing if you want from 0 to 2 pi. So do half of it double, or you can do the whole thing. Okay, number 14, write but do not solve an integral expression that represents the area enclosed by a smaller loop. So anytime we're talking about a loop that's closed off or a petal that's closed off, you know you're always looking for petals. You're always looking for polar zeros. Polar zeros, consecutive polar zeros will tell you the region that you're looking for. So by polar zero, I just set my r equal to 0, solve for theta. I get sine is equal to 1/2. That's in the first and second quadrant. So pi over 6 family here. So pi over 6, pi over 6. And then just do the definite integral from 1/2 integral theta 1 to theta 2 r squared d theta. Number 15, find the limits of integration to find the area of one petal of polar graph in the second quadrant. So I was just picking r values, or sorry, theta values. This is, I meant to be theta comma r. Theta values that I knew to be true with, I knew that this has 3 petals, that this was going to go from 0 to pi to complete. So if I divide that by 3, I'm going to get pi over 3, 2 pi over 3, and pi. So I should knew between 2 pi over 3 and pi would work. But another way we can do this is, why don't we just find all the polar zeros, and then we just identify all the intervals that's in the second quadrant. So we can just set 4 sine 3 theta equal to 0, divide by 4, take the inverse of sine to get that 3 theta by itself, inverse sine of 0. In other words, where is sine equal to 0? So sine is equal to 0 at 0, pi, 2 pi, 3 pi, 4 pi. And if I divide by 3 or multiply by 1/3, I can get my theta values. So these are the actual theta values where my Rose curve is going to hit the polar zero. So at 0, pi over 3, 2 pi over 3, pi. And I'm looking for something that is in that 2-second quadrant range. So between 2 pi over 3 and pi is where I can, I know that to be true. Okay, page 13. What is the total area between the polar curves of r equals 2 sine 3 theta and r equals 5 sine 3 theta? The nice thing is that these are both going to be 3 petals. They're both sine. They're both having the same polar zeros, just that one has a longer petal length than the other. Okay. So if we have our graph drawn here, we know that the polar zeros that form the first quadrant is going to be at 0 and pi over 3. I can set either of them equal to 0, r equal to 0, and solve for theta. I'm going to get 0 and pi over 2, and then pi over 2 times 1/3 will be, I'm sorry, it becomes 0 and pi, and 0 and pi times 1/3 will be 0 and pi over 3. So we know our interval is from 0 to pi over 3, and the idea is that if we find the area of the large petal and then subtract the area of the inner petal, smaller petal, then what's left is the region between the two petals. So the idea that if we take the area of the large petal, so then that represents the 1/2 integral from 0 to pi over 3 of the big of the r 5 sine 3 theta quantity squared d theta. And then minus, if I subtract out the smaller petal, so again from 0 to pi over 3, and what's left is this outer region here. Okay. It says find the total area between the polar curves. So there's 2 other petals that have the same situation. So I can find the area of this, multiply it by 3, and I can get all the regions that we need. Yeah. Well, see, the problem is that I don't know if 0 to pi will work because this complete the cycle at pi. So I would just go from maybe try from 0 to pi and then from 0 to pi. Right. But that's true. That's true. You can, yeah, I think try that. That should work. My philosophy is I like to find the smallest region possible and then multiply by whatever I need because of symmetry, rather than depending on looking at the whole graph. So I like to do the smallest region possible and then multiply that out. But yeah, your way works too. I think the reason that I like to do this way is because especially if something feels more complicated when there's like a bunch of switches between graphs, rather than to do that all the way throughout multiple quadrants, I just do, with the smallest region possible and then multiply it by however much. Yeah. But I think that should work. You should test it and try it out, and we should get the same answer. But yeah, make sure you go from 0 to pi, since this, if it's an odd n theta, then we should be able to complete the cycle from 0 to pi. That won't take as long as 2 pi. Well, they're both sine and they're both odd, and they have the same number of petals, so they're always going to share the same bounds.
No, but I'm saying, like, let's say if you solve for the polar zeros, would that always be the bounds for like the individual?
Yes, yeah, your polar zero will always be the bounds if you want to find one petal or one inner loop. Yeah. Thank you. Oh, you need close parentheses for y1. Yeah.
Sorry,
Everything else looks good, yeah. Yeah, so this one, no, they're telling us what the bounds are. And so from negative pi over 2 to pi over 2, one cycle completes for both of these equations. And so really it's just the area of the larger minus area of the smaller. So we take the bounds that they give us, area formula for the larger minus area of the smaller, and that will give us that region that's between the two curves. Okay, number 18, find the total area in the first quadrant in the common interior of R equals 4 sine of 2 theta. So what we can do here is, first off, we see that we need to find the intersection, because at this intersection is where there's a transition, right? That means from 0 until pi over 12, we're hitting the petal, the rose curve. And then from pi over 12 onward, we're hitting the circle. So we can do this as 3 integrals if you want. We can do the petal, and then from the petal to the circle, and the circle back to the petal. But I just like to get the smallest region that I can, and then use symmetry to figure out the rest. So from 0 to pi over 12, I know that I'm hitting that 4 sine of 2 theta. And then from pi over 12 to the halfway point of my rose curve is going to complete its first cycle at pi over 2. So halfway point is going to be at pi over 4. Another way that we can do this is that we know that this point is when R is equal to 4. When R equals to 4, my theta is going to be pi over 4, because I can just work that out algebraically as well. So if I can find the area of those two red and green regions, I can take that, double it, and then that will be the area of the common shared region in the first quadrant. Okay, number 19. Find the area of the common interior. So I found the intersection first, because I know that as I'm sweeping through, that I'm hitting different graphs, right? So up until the intersection, I'm hitting from 0 to that intersection, I'm hitting the the first circle. And then from pi over 4 to pi over 2, I'm hitting the second circle. So I need two integrals. Some students have said, why can't we use symmetry? I think in this case, maybe you can use symmetry, but just to be safe, I just used, because, let's say this was a circle that had a different dimension, different width, then we can't use symmetry. So, but yeah, technically, because these are the same circles and they're symmetric to each other, we can use symmetry. You can just do half of this and then double it. That could work. But the full region here, you can also spell it out from 0 to pi over 4 of one graph and switch over from pi over 4 to pi over 2 to the other curve, the 3 cosine. And then number 20, we have the polar curve, r equals cosine theta, that's the circle. And then we also have 7/2 theta, that's this curve here. The two curves intersect at theta equals 0.275 radians. What is the area of S? So area of S is the shaded region, but the shaded region, if we want to build out from a polar perspective, then as we radiate out from the origin, we see that from 0 until 0.275, we're hitting the curve that I highlighted in green. But then from 2.275 until pi over 2, I'm hitting the circle. So I need two separate integrals to adapt for these two distinct regions because they're not, I need two separate integrals since they're the regions are made up of two separate graphs. Okay. Let me know if you have any individual questions.
Mr. Do all unisons, like regardless of the A and B, like if they're the same or one's bigger than the other, do they all go from like 0 to 2 pi?
Yeah, they do.
Always.
How'd you draw that so well? How'd you draw that so well? I just a little.
Oh.